Okay, so welcome to today's class. So today we will discuss about modern block cipher standards. So in last day's class we have discussed about the DES algorithm, and so today we will take up a new standard, or rather which is followed worldwide, and it was adopted as a standard from 2000, around 2001, and that is, the algorithm is known as the advanced encryption standard, but the name of the algorithm is Rijndael, given by the names of the designers of the algorithm. So today's objectives are as follows. We shall discuss about finite fields, because finite fields form a very important component of the AES algorithm, and it is important to understand the field theory or finite field theory in order to understand the intricacies or the internal workings of the algorithm. Then after an introduction to the finite fields, we shall discuss about the internal algorithms or the algorithm steps of the AES algorithm. So essentially AES has got 4 steps, like the sub-byte step, the shift row, mixed column, and followed by add round key. So talking about finite fields, a finite field is a field with a finite number of elements. So the number of elements in the set is called the order of the field. So and therefore essentially what we are talking about here is that we know that we talk about integer numbers, for example. So therefore in case of integers we essentially do operations like addition, multiplication, but the number of elements that we have, for example in the integer set, is infinite. But on the contrary, in case of finite fields we shall have finite number of elements. So that means that we have to do our multiplication operation, our addition operation, using in a set which has got finite number of elements. So that has got natural consequences, as we shall see in our further in this class itself. So a field with order m exists if and only if m is a prime power, that is m is equal to p power n for some integer n, and where p is a prime integer. So in case of finite fields, we essentially refer this variable p as a characteristic of the field. So therefore we shall see, as we shall see in our discussion on the AES algorithm, the characteristic of the finite field of the AES algorithm is p equal to 2. So therefore we shall find that the internal field of the Rijndael algorithm or the AES algorithm is gf 2 power 8. So finite fields are often referred to as the Galois field also, and it is denoted by the letter gf. So therefore gfp means that essentially that we have got the number of elements that are there inside the gfp are from 0 to p minus 1, that is 0, 1 to p minus 1. So the elements of the fields can be represented as 0, 1, comma p minus 1. So in this case the point to be noted is that if p is not a prime number, then multiplications are not defined. So this follows from a natural result from number theory, which says that the multiplicative inverse of an element a modulo m exists only, rather if and only if the GCD of a and the modulo m is equal to 1. That is, what I mean to say is that when I am considering the numbers inside, say, a modulo m, and I am considering the letter, I am considering the inverse of a modulo m, that is a inverse modulo m, then a inverse modulo m exists if and only if the GCD of a and m is equal to 1, that is a and m are mutually co-prime. So this result follows from the Euclidean theorem, which we shall see in our future classes, but right now let's accept this as a result, and it says that, so therefore the idea is that if p is a prime number, then all the elements starting from 1 to p minus 1 are essentially co-prime with p, and hence every element has got a multiplicative inverse, and thus that fulfills the criteria or definition of a field. But if p is not a prime number, then multiplications are not defined. So therefore the inverse of an element, that is a multiplicative inverse, may not exist. However, when we are considering, say, finite fields like gf p power n with n greater than 1, then if we use slightly complex representations, then actually we can define the idea of a field as well. So in that case we shall see that the elements in this case have to be represented in a form which is called which is basically a polynomial notations. In that case we can do our multiplication as well as our addition operation. So how does a polynomial over GFP look like? So it looks like this. So if consider a polynomial over a field f, and it can be denoted by an expression of the form bx is equal to bn minus 1 x to the power of n minus 1 plus bn minus 2 x to the power of n minus 2 plus so on plus b0. So x being called indeterminate of the polynomial, and the bi, that is the coefficient of this polynomial, are essentially belonging to the underlying field. So therefore when we consider a polynomial in gf 2 power 8 for example, or rather gf 2 power n, then each of these coefficients would belong to the field gf2. So that means each of these coefficients in this case has got now the elements that gf2 has got are zeros and ones. So which means that when I am considering a gf2 power n polynomial, then the coefficients are either 0 or they are 1. So here x is often referred to as the indeterminate of the polynomial, and there is a term called degree which we know, for example, for polynomials. So we say that a polynomial has got a degree L if bj, that is the coefficient bj, is equal to 0 for all j which is greater than L. So therefore L is the smallest number with this property. So that means the set of these polynomials over a field is referred often by this notation fx, and the set of polynomials over a field f which has got a degree which is less than L is denoted by fx suffix L. So that means fx suffix L means that I am referring to the set in the entire set of the polynomials over a field f whose degree is less than L. So another importance of this particular notation when I am talking about in Galois fields or in finite fields is that this polynomial can be stored in the form of a register. So therefore if we would like to represent this in a say on a computer, then we can store this in an array where each of these elements would have belonged to this underlying field f. So what happens when we are referring to the field gf2 power n? The entire polynomial can be stored in an n bit register where each of the bits essentially are either zeros or 1. So therefore we see that this representation in gf2 power n has got a very natural linkage or connotation with the normal computer arithmetic, and therefore that is the precise reason why gf2 power n arithmetic is essentially very easily amenable to nice computer architectures. So we can have nice multipliers, nice inverse architectures, which essentially leads to highly efficient architectures for cryptography, for communication, and that is the precise reason why this field gf2 power n has got lot of interesting applications in both communications as well as in cryptography. So the moment we have these polynomials, so what are the polynomials? The polynomials are essentially elements of a field. So what is our objective? We essentially would like to define addition and multiplication operation on these polynomials. So how does an addition works? It's quite simple. So if you would like to do an addition over the polynomial ax and bx, then how do you obtain cx? Is a simple addition, but that means that for every I, what we are doing is just adding the coefficients. So you take ai, you take bi, you add them, and you store them in the form of ci. So that you do for all from 0 to n, 0 to n minus 1. So therefore that is for all the values of I. So the point to be noted here is that addition is quite closed. That is, if I take for example a degree, for example consider the degree of ax is say greater than the degree of bx, then the degree of ax plus bx cannot be greater than that of the highest degree of between ax and bx. So that means the degree of cx is always lesser than the higher degrees of between ax and bx. So that means cx is always closed. That means addition is essentially closed. And also we note that if we, for example, if we have one of the polynomials with all their coefficients as 0, and that we often refer to as the element 0, then 0 forms the identity element under the addition operation. and the inverse of an element can be found by replacing each coefficient of the polynomial by its inverse in f. So therefore, for example, that if you take any element, that is, for example, if you take the element say ax, and I would like to form the inverse of ax, that is, I would like to compute the inverse of ax under the addition operation. So how do we do that? So what we do is that, for example, let us consider the example of GF 2 power 8. So in GF 2 power 8, an element ax can be referred as, or rather written as, a7 x to the power of 7 plus a6 x to the power of 6 plus so on till a0. So I need to form the inverse of ax, which means that if, for example, this is, say, let this be equal to bx, then ax plus bx should go to 0. So when I am forming bx also I can denote like b7 x7 plus b6 x to the power of 6 plus so on till b0, and therefore if I would like to satisfy this equation ax plus bx is equal to 0, then automatically it means that I have the identity that a7 XORed with b7 is equal to 0. This implies that a7 and b7 are essentially the same things. So that means what? That means when I am trying to form the inverse of ax, that is the additive inverse of ax, then in order to do that, I replace each coefficient of the original polynomial ax by its additive inverse in the field GF2. So in GF2, for example, every element is self-inverse. Like, what I mean to say is that in GF2 you have essentially two elements, 0 and 1, and 0 is the self-additive inverse of 0, and 1 is the self-additive inverse of 1. Why? And because 0 XORed with 0 is equal to 0, and 1 XORed with 1 is also equal to 0. So therefore, coming back to our operation on polynomials, we can see that when I am talking about addition, I mean forming the inverse of an element, then the inverse of an element can be formed or can be found by replacing each coefficient of the polynomial by its inverse in f. And then we say that fx under the fxl, rather, because I have already defined what fx suffix l means. Fx suffix l, this set of polynomials with their degree l under the operation addition forms an abelian group. Why an abelian group? Because it's also commutative, that is a plus bx, like, or ax plus bx is equal to bx plus ax. So it's as well as it's also commutative. So what about multiplication? So it's not so straightforward in case of multiplication, but before going into multiplication, let's consider one example for addition. So let f be the field in GF2, and we would like to compute the sum of the polynomials which are denoted by 5, 7 and 8, 3. So first of all, let us denote 5, 7 and 8, 3 in binary notation. So this is how it looks like. So in polynomial notations, I can express 5, 7 as this. So I think all of us are convinced, because you see that this one forms the coefficient of your constant, this one forms the coefficient of the variable x, this one forms the coefficient of x square, and then the coefficient of x power 3 is 0, so therefore you don't have an x power 3 term here, but here you have 1, so essentially that forms your, so this one forms your x power 4, and this one forms your x power 6. So you can see your x power 7 and x power 8, or the x power 7 and x power 5 are the coefficients of them are still are missing, because you have 0 as the coefficients. So the polynomial becomes, in the polynomial notation, your number 5, 7 can be represented as this, and your 8, 3 can be represented as x to the power of 7 plus x plus 1. So I need to do the addition operation among these polynomials. What I do is that I arrange them considering their degrees, and then, for example, this is quite straightforward, that you get x power 7 because you don't have an x power 7 term here. You have x power 6 and you don't have an x power 6 term here, so you get x power 6. Similarly, x power 4, there is no x power 4 here, so you get x power 4. What about x power 2? X power 2 also, there is no x power 2 here, so you get straight over x power 2 here. And consider the variable x, there is an x here and there is an x here. So when I am considering x, I am essentially doing an addition over GF2, which is the underlying field, over the coefficients of x in both the terms that I am adding. So therefore there is a 1 here and there is a 1 here, and if I do an XOR between them, I essentially get 0. So x does not appear in the sum. Similarly for the constant term. So finally your result is x power 7 plus x power 6 plus x power 4 plus x power 2. And you note that addition can be implemented with the simple bitwise XOR instruction. So the addition in the field GF2 power n can be implemented with the simple bitwise XOR instruction. So addition is quite easy if you are able to remember that when you are adding terms, then you also need to do the modulo 2 operation. So for example, this may sometimes seem to be quite strange to us. For example, if I would like to compute the sum of say x power 1 rather x plus 1 whole square, then that essentially would result in, so consider in addition GF2 power 8, and I would like to form the sum say x plus 1 XORed with x. Okay. So in normal addition, so if this would have been a normal addition, then we would have got 2x plus 1. Okay. But when you are doing an addition over the GF2 power 8 field, then you need to do, what you need to do is that do a simple addition, but over the coefficients you do a modulo 2 operation. So if you do a modulo 2 operation here, 2 gets reduced to 0 and you get back 1. So therefore that is how you can easily obtain the corresponding sum. But multiplication is not so straightforward. So in case of multiplication, the properties of associativity and commutativity are quite easily to understood. But what about, and also distributivity with respect to the addition of polynomials. Okay, so I think we all of us know these points, and these things are quite self-evident. But what about multiplication? The problem, or rather the difference of multiplication from addition is that in case of multiplication, there is a problem of overflow. So when you are multiplying, say for example, two n degree polynomials, then your resultant output, that is the product, has got a degree of more than n. So therefore if your field is restricted, then there is a problem of overflow. Which means what? Which means that in order to do, or rather impose the property of closure, we require to do a modulo operation. So therefore in order to do a modulo operation, we essentially introduce the concept of a reduction polynomial, and that is denoted by mx, whose degree is L, and I call that a reduction polynomial. So that means when I am doing a multiplication, then I define my multiplication as follows. I take ax and bx, and if I want to do a multiplication and obtain cx, it implies that I do a normal multiplication over with ax and bx, a normal polynomial multiplication, but I do a modulo with mx. So the idea is that I require to bring the corresponding product back to my field. So if you are able to do that, then your fx L or fx suffix L under the operation of both plus and dot is essentially a commutative ring. So basically what you have done is that you have imposed the property of closure and you have obtained what is known as a commutative ring. Okay, but for special choices of the polynomial, this mx essentially leads to the structure of a field. So what is that property for a polynomial mx? So we essentially need a property which is known as irreducibility. So what is the extra criteria that we require when we are talking about say a field? We require the idea of a multiplicative inverse. So the moment we require something which is called a multiplicative inverse, so if you remember our normal number theory, then essentially we had the result that that number had to be a prime number. So what I mean to say is that if you consider the numbers from say 0 to say 0, 1, 2 and 3, 4 and say 5. Okay. So if I exclude 0 and I take only the elements say 1, 2, 3, 4 and 5, then essentially I am doing a modulo 6 operation. Okay. So you see that in this case all the elements we have already discussed in our previous class does not have a multiplicative inverse. For example, 2 does not have a multiplicative inverse, that is 2 inverse modulo 6 is not defined. Why? Now because the GCD of 2 and 6 is not equal to 1, that is 2 and 6 are not co-prime to each other. So similarly, when you are doing your, if you require to define this, then instead of taking a modulo 6, I would have rather taken modulo 7. Why? Now because 7 is being a prime number, all the elements from 1, 2, 3, 4, 5, 6 essentially are co-prime to the number 7. So therefore, the idea of a primality or prime modulo was important to define the concept of multiplicative inverse of all the elements. So in order to have a multiplicative inverse for all the elements, we required that our modulo had to be a prime number. So similar concept exists for our polynomials also. So in case of polynomials, we replace our prime modulo, and rather we call our prime modulo by an irreducible polynomial. So therefore, let's go through the definition of irreducible polynomial. It says that a polynomial dx is irreducible over the field GFP if and only if there exist no two polynomials ax and bx with coefficients in GFP such that dx is equal to the product of ax and bx. So that means that ax and bx form the product or form the factors of dx, and their degree is greater than 0, but it is essentially less than the degree that we are considering, like for example the degree of the field. So therefore these elements, that is ax and bx, should not be members of the field. So therefore there should not be any factor of dx which is in the field. So such kind of factors are not permissible. So that forms the definition of an irreducible polynomial. So for example, let f be the field GFP with suitable choice for the reduction polynomial, the structure fx suffix n, and under the operation of plus and product is a field with p power n elements, and it is usually defined or rather denoted by the letter gf p power n. So in case of AES, p is equal to 2 and n is equal to 8, and therefore we are talking about the field gf 2 power 8. So there are some examples of irreducible polynomials. So consider degree 1. You see that x plus 1 and x are irreducible in this field because you do not have any factors of x plus 1 and x which are inside, or rather which has inside this field. Okay. So consider, for example, I think this will become much better explained if you take the degree 4. Okay. So here are some polynomials in gf power for gf 2 power 4. So if you consider gf 2 power 4 and say take this particular polynomial x power 4 plus x plus 1. Okay. So therefore you will consider the field gf 2 power 4 and consider a polynomial whose degree is 4, x power 4 plus x plus 1. So if I say that this particular polynomial is an irreducible polynomial, then what we have to show is that x power 4 plus x plus 1 cannot be written in this form, ax into bx, such that the degree of ax or the degree of bx is less than 4. So the degree of ax or the degree of bx should not be less than 4. So consider another example like x power 4 plus 1. The question is this an irreducible polynomial? So we can see that, for example, x power 4 plus 1 I can factor as x plus 1 whole power 4. Why? Because if I do a normal multiplication like x plus 1 whole to the power of 4 and apply a modulo 2 operation over all the other coefficients, then we will see that only x power 4 plus 1 remains, whereas the other coefficients are even numbers, and therefore if I take a modulo 2 operation, they all of them goes to 0. So therefore this particular factorization holds in this field gf 2 power 4. Okay, so therefore this holds. So therefore we see automatically that x power 4 plus 1 has got a factor x plus 1 which essentially is a member of the field GF to power 4. So that means that x power 4 plus 1 is not an irreducible polynomial. So therefore, if I want to define the idea of a field, that means if I want that all the elements, or rather all the elements except 0 has got a multiplicative inverse in GF to power 4, then I require to have my reduction polynomial of this type, maybe this, but not this. So this is not a good reduction polynomial if I would like to define the characteristic of a field. So here are some other examples which you can see that they are really irreducible or not reducible. So you can take it as an exercise also. So now let us see how a multiplication works. So if I still want to compute the, if I want to compute the product, and we take the same examples as we have done for the addition case, we take 5, 7, and 8, 3, which are members of GF to power 8, and we have the same binary notation. And in polynomial, this is I have already described how this works out, how this can be represented in this form. So suppose I would like to compute the product of this polynomial and this polynomial. So in order to do that, we just do a normal multiplication, that is as I would have done with fields, with finite fields or without finite fields, just keeping in mind that our addition is an XOR operation. So if I do that, then this is the final polynomial that I get, and the moment I need to have a reduction polynomial, because we see that the highest degree term is in this case x to the power of 13, and x to the power of 13 does not belong to GF to power 8. So in order to bring it back to GF to power 8, we require to do a modulo with a reduction polynomial. And the reduction polynomial that we have considered here is x power 8 plus x power 4 plus x power 3 plus x plus 1. Why? Because this is an irreducible polynomial in this field. So if we do a modulo with this field, then we get back x power 7 plus x power 6 plus 1. So therefore we see that we have essentially brought back our result back to the field GF to power 8. And actually, as a matter of fact, that this is the polynomial which is being used in AES, or in the description of AES, as an irreducible polynomial. So summarizing, or rather commenting about the advantage of addition and multiplication in GF to power n, we have already reflected upon the fact that addition can be implemented using only the XOR operation, but in case of multiplication can be implemented, but you cannot do that only with the XOR operation, but you require to do another operation, which is the simple shift left operation. So in case of normal multiplication, you could have done with normal shift left, but since you are doing a finite field multiplication, you require to do some extra XOR operation, because you require to bring back the back to the field. You require to do a modulo operation. So we shall talk about a concept of something which we call as generator. So it is often easy to define the elements in the field using a generator. Okay. So what is the idea of a generator? So the idea of a generator, or why generator is required, is as follows. That is, what we require is that all the elements which are there in the finite field, I would like to generate them by using a single element. So therefore I take a single element and I call them, say, G, and I consider the various powers of G. So therefore, for example, I consider G, I consider G square, I consider G cube, G power 4, and so on, and I would like to generate all the elements in the finite field. Obviously you understand that 0 cannot be generated, so therefore all the non-zero elements, can they be derived in this fashion? So that is the idea of generators. This particular element G is often referred to as the generator or the primitive element of the field. So in our case, if you consider the irreducible polynomial, say fx, and I say I need to compute the value of the generator G, then what I do is that I solve the value, I solve this equation fx equal to 0, and I obtain the generator. It can be actually proved that all the elements of the field GF to power n can be expressed in this form, like I take 0 and the others I generate by G, G square, G power 3, and so on till G power n, where n is equal to 2 to the power of small n minus 2. So n was essentially, 2 to the power of n was was essentially, so when I am considering a field of GF to power n, then I have got my elements which I can represent from 0 to 2 to the power of n minus 1. So therefore 2 to the power of n elements exist. So in our case, we note that we have ran n till 2 to the power of n minus 2. Why? Now because there is a theorem called Fermat's little theorem which says that if you take an element G and if the number of elements in the field is P, then G power P minus 1 is equal to 1 when you are doing a modulo P operation. So if you consider the field say GFP, then all these elements were so therefore if you consider all these elements and you take G, which is a generator, so I call G as a generator, okay, then G power P minus 1 is equal to 1 when you are doing a modulo P operation. So that means that if you consider all the elements, for example, that if you just consider the fact that if I just take 0, so 0 is 0, you take G is equal to G, you consider G square is equal to G square, okay, you take G power 3, it is equal to G power 3, but for example if I just consider, if I consider the field GF2 power 4, then if I consider the power G power 4, we have a problem of overflow because G power 4 essentially cannot fit in the field GF2 power 4. So we require to do a modulo operation, and therefore if I take say for example x power 4 plus x plus 1 as my corresponding irreducible polynomial, so x power 4 plus x plus 1 was an irreducible polynomial, we have already seen that. So in that case, if we know that G satisfies fx equal to 0, then fg, this implies that fg is equal to 0, which means that G power 4 plus G plus 1 is equal to 0, and therefore it means that G power 4 is nothing but equal to G plus 1. Why is G power 4 equal to G plus 1? Because the addition in case of a GF2 power n field is nothing but a subtraction operation. So if G power 4 I would have transferred this on the other side, and if I just take addition and subtraction to be the same, then I obtain this result. Another way of observing this would have been this, that is G power 4 plus G plus 1 equal to 0. If I add G plus 1 to both sides, then I get G power 4 plus 2G plus 2 equal to G plus 1, and if I apply modulo 2 operation over these coefficients, then all of them go to 0, and what I obtain is G power 4 equal to G plus 1. So that means that this G power 4 I could have represented as G plus 1. Similarly, if I would like to compute G power 5, then G power 5 is G into G plus 1, so that is equal to G square plus G. So that is still inside the field. Okay. So another way of seeing that it is really in the field is that I would have, in order to represent elements in GF2 power 4, we already discussed that we can represent them in the form of polynomials, and therefore we can, and also the corresponding binary representation would involve 4 bits. So that means any 4-bit number can represent, using a 4-bit representation, I can represent all the polynomials in GF2 power 4. So consider 0, it can be expressed as this. What about G? I can express this as 0, 1, 0. What about G square? I can represent them as 0, 1, 0, 0. G cube, I can represent them as 0, 1, 0, 0. But G power 4, I cannot represent in 4 bits, so that means there is an overflow. But if I do this modulo operation, I obtain G plus 1, and therefore that can be represented as this. What about G square plus 1? I can represent G square plus 1 as 0, 1, 1, and 0. And so I can obtain the other elements also. But the point that I was saying from Fermat's little theorem is that we will see that G power, so if I consider 2 to the power of 4 minus 1, then that is equal to 15. So we will see that G power 15 is actually equal to So if I keep on multiplying in this fashion, so we will see that d to the power of 15 is actually equal to 1. So that means if I would like to find out all the elements, then after this I have got a circular shift, because what is the next element after this? I obtain g, because I again multiply this with g and I obtain back g. So that means that all the elements in this form essentially form a cycle. So therefore if I start with g and I obtain g square, okay, so if I start with, say, then I obtain g power 3, I obtain g power 4, I obtain g power 5, okay, and similarly if I continue like this, there is a point after which g again reappears. So there is a 1 which appears at one place, so there is, say, g power 14, after which there is a repetition. So therefore there is a cycle. All these numbers can be represented in the form of a cycle. So this is also called a cyclic order or cyclic field. So therefore if I would like to represent all the elements, then I can represent all the elements in this form: 0, g, g square, g power 3, and so on till g to the power of n. Okay, so where n is equal to the power of n minus 2, and if I consider the next element, then I obtain back g. Okay, because that is the, I mean, that follows straight away from the Fermat's little theorem. So this could be one exercise, rather which I have solved already, that generate all the elements of the fields in GF2 power 4 using the irreducible polynomial fx equal to x to the power of 4 plus x plus 1. So this, if I would like to generate all the elements of the field GF2 to the power of 4 using the irreducible polynomial, so then these are the corresponding elements. Okay, so next we come to the introduction, the real AES algorithm, or the advanced encryption standard algorithm. So in 1999, NIST essentially issued a new standard that said that 3DS should be used. So we have already seen that in case of 2DS there were certain vulnerabilities, and 2DS was not able to provide the security of 112 bits of key because of the meet in the middle attack. Okay, so therefore what it was thought is that 3DS will be adopted as a standard, and therefore 3DS was essentially supposed to provide a security of 168 bit key lengths. Okay, and the algorithm was same as DES, but there are some weaknesses. The weaknesses was that the algorithm was quite sluggish in software, and at the same time it uses only 64 bit block size. So therefore, and also in case of DES we have seen that there is something called weak keys, and those keys still existed for 3DS. So therefore 3DS was supposed to be substituted, and NIST issued a call for papers, or call for a new cipher. So therefore people thought around the world that there was a necessity of something which is called a standard, like an advanced encryption standard. So the criteria for the AES algorithm, or rather for the cipher which will be adopted for as an AES, essentially were as follows. The security strength should be essentially equal to or greater than that of 3DS. The efficiency should be improved, and it must be a symmetric block cipher. So therefore the blocks and the block length should be either 128 bits or more than 128 bits. So therefore it was supposed to be a symmetric block cipher of 128 bits, and the key lengths that it needed to be supported were of 128 bits, 192 bits, and 256 bits. So initially in the first round of evaluation, around 15 proposed algorithms were accepted, and in the second round 5 proposed algorithms passed this round of selection, and the 5 algorithms were Rijndael, Serpent, Twofish, RC6, and Mars. Finally, in November 2001, Rijndael was selected as the AES algorithm. So in case of AES algorithm, we will see that in case of AES, all the block lengths essentially are taken to be of 128 bits. So we have got AES 128, AES 192, and AES 256. So the basic data of AES is often represented in the form of something which we call as a state matrix. So how does the state matrix look is as follows. So we can represent them in the form of this matrix. So for example, let us consider AES 128. So each element of this state matrix is a byte. So the number of rows is always equal to 4, but the number of columns vary. So we say that the number of columns is represented by the letter NB, by the variable NB. So for AES 128, the value of NB is equal to 4. So which means that we have got 16 bytes. So that 16 bytes means what? We have got 16 into 8, that is equal to 128 bits. So therefore the AES data block in case of the AES 128 is equal to 128 bits. So what about AES 192 and AES 256? In case of AES 192 and AES 256, your block size is equal to 4 and 4. So which means that in all the three cases of AES 128, 192 and 256, your data word is actually equal to 128. So therefore you are always processing a 128 bit of data. 128 bits of your block size is always 128 bits. But what about the key? So you note that your key actually in case of AES 128 is actually 128 bits, here it's 192 bits, and here it's 256 bits. So the key also can be represented analogously by another state matrix where your number of rows is still 4. You can again represent this in the form of a matrix, and your number of columns is denoted by nk, but nk is actually not only equal to 4, but it is equal to 4, 6, 8. So in case of AES 128 it is 4, in case of AES 192 it is 6, and in case of AES 256 it is 8. So that means the total size of the key is either equal to 128, that is 4 into 4 is equal to 16. So therefore you have got 16 bytes, means you have got 16 into 8. So therefore total number of bits works out to 128 bits. But in case of AES 192 and in case of AES 256, the number of bits is 192, and in case of AES 256 it is 256 bits. Another point to be noted is that the number of rounds also vary. That is, in case of AES 128 the number of rounds is 10, in case of AES 192 the number of rounds is 12, in case of AES 256 the number of rounds is 14. So there are specific requirements why the number of rounds were fixed like this, but that follows from deep cryptanalytic results. We shall see we shall again discuss about this point in our future class. So the difference, so AES and Rijndael are not essentially the same. Rijndael is a block cipher where both the block length can vary as well as your key length can vary. So therefore Rijndael is a block cipher where both the where both the block length and your key lengths can vary. But when we talk about the AES structure, so in case of AES your block length is actually fixed to 128 bits, but your key lengths can vary, and it can be independently varied from 128 to 256. So therefore you see that in case of Rijndael it's a block cipher with both a variable block length and a variable key length, but in case of so therefore Rijndael is a block cipher where the block and the key lengths can be independently fixed to any multiples of 32 ranging from 128 to 56 bits. But in case of AES the block length is fixed to 128 bits, and therefore it supports key lengths of 128, 192 and 256. So that means that the difference between Rijndael and AES is that in case of Rijndael you can also vary the block length, but in case of AES your block length is fixed to 128 bits and your key is essentially only 128, 192 and 256. But in case of Rijndael your key lengths also could be fixed to any multiples of 32 ranging from 128 to 256. So you have intermediate values as well in case of the Rijndael algorithm. So Rijndael is a more generalized cipher, but out of them only those configurations which were tested for the AES competition essentially form what we know as today's standard or today's advanced encryption standard. So this is how the Rijndael algorithm works. So you have got your input bytes and you transform them by certain operations to your output bytes, and the intermediate steps you store in the form of something which we refer to as the state array. So you see that in this case we are talking about the AES in fact, and you have got 16 bytes, so we denote them as in0, in1, in2, in3. So you store them in the form of through the columns. So you have got in0 to in15 bytes. Similarly, you have got out0 to out15 bytes, but in between the corresponding steps, the corresponding operations that you do in the Rijndael algorithm transform these input bytes to the output bytes, but the intermediate values are stored in the form of a state matrix. So all the rounds of the Rijndael algorithm transfers these state matrices. Okay, so therefore they perform operations on the state matrices. So one of the prime reasons why Rijndael essentially or became the AES, or rather the AES was won by the Rijndael designers, was that essentially this particular algorithm has got a nice byte-wise representation. Okay, and the nice byte-wise representation led to good implementation features on even 8-bit processors. Okay, so therefore, I mean, we will discuss in our next class that in case of AES we actually derive very good performance over various range of platforms. Like you take 8-bit platforms, you take 16-bit platforms, you take 32-bit platforms, or you take even higher bit platforms. The AES platform, the AES algorithm works quite well, so it derives quite good performance, and that is one of the reasons is that it has got a nice byte-wise. I mean, the transformations can be expressed through byte-wise operations. So looking inside the Rijndael algorithm, so in Rijndael each round has got 4 functions. So there are 4 round functions. The first one is called Byte Sub, then you have shift row, then you have mix columns, and then you have add round key. Okay, so let's discuss one by one. So first Byte Sub. Byte Sub forms what we know as the S-Box. So therefore this is the only nonlinear step in the Rijndael or AES round function. So what you do is that you take each byte and you pass that through an S-Box. This S-Box is an bijective transformation, which means it's a 1-to-1 map. So it takes an 8-bit input and it produces an 8-bit output. So it takes, for example, SRC and converts that into another byte. So it takes a byte and produces a byte, and that is essentially exported to the output of this step. Okay, so this Byte Sub is based on the mapping which was defined by Nyberg and published in Eurocrypt 1993, and it is based upon a paper which was called differential uniform mappings. Okay, so therefore the input in this case is an 8-bit value A, and here A is in GF2 power 8. So the S-Box is based on a mapping that if you take A and you produce B, and what you do is that if A is equal to 0, you take 0 as the output. That is, as we have already discussed, that all the elements apart from 0 have got multiplicative inverse. So which means that if you take A and A forms your one of your elements, then the output is denoted by A inverse. But if A is equal to 0, then since inverse is not defined, in order to define at that point, we say that the output is also 0. So we define that 0 inverse is 0. Okay. So therefore, if you through this definition from A you can obtain B. So therefore, this is a mapping that we have taken from A to B. Okay, and there are nice properties of this mapping, so which we shall discuss in our cryptanalysis classes. But this mapping has got a property which is called a very uniform kind of nature. So there is a very uniform transformation of these elements. So in addition, the designers also wanted that there should not be any fixed points or opposite fixed points. So that means that what was desired is that if you take A as the corresponding input and you apply the Rijndael S-Box, and then you take and you XOR that with A, then you should not get either all zeros or FF, that is all ones for all values of A. Okay, so I call this as the fixed point and we call this as the opposite fixed point. So in order to achieve this, an affine mapping was defined. So all of us have seen what is an affine cipher. So you see that similar concepts appear in the case of in case of modern ciphers as well. So how is that affine? How does the affine mapping look like? What it does is that it takes the corresponding output of your inverse function and passes that through a matrix, which I referred that as a big matrix A, and this is a vector called B. Okay, so you note that if you denote this in this form, and this, if you observe this corresponding mapping, then you will see that each of these rows has got almost the equal number of zeros and ones, so we can make this observation, whereas the other rows are just cyclic permutations. Okay, so you see that this particular matrix has got the property that all these rows are linearly independent, and therefore this matrix has got a full rank. Why is that required? Because we require to do the we require to have this, we require the fact that this particular matrix should also have its multiplicative inverse, because if its multiplicative inverse does not exist, then we cannot obtain back A, the vector A, from the vector B. And where is that required? Because we require to decrypt also what we encrypt, right? So therefore we see that if we take the so if I combine these two steps, the AES S-Box looks like this. So your AES S-Box works on 8 bits and it produces another 8 bits of output, right? So what you do is that you take, for example, A and you produce SA, okay, and I call that SRDA. Okay, so how is SRDA obtained from A? So what you do first is that you take A and you obtain, or rather pass it through the mapping G. Okay, and we have already defined how GA works. You represent that you obtain either A inverse if A is not equal to 0, or if it's A equal to 0, then you straight away pass 0. And then what you do is that you take this value of GA, since this is also an 8-bit number because it belongs to GF to power 8, I can multiply this, or rather represent this 8-bit number in the form of a vector of 8 rows and 1 columns, and multiply that with a matrix which I call as A. So therefore what we do is that you multiply this with a matrix of 8 cross 8 dimension, and that is called A, and you add that to another vector which we call often as B, and also this has got a dimension of 8 cross 1. Okay, and if the inverse of A, and this output is essentially what we call as SRDA, or we call that B, for example. So now given B, how can we obtain back A? Okay, so we can easily see that we can obtain this, right? Because B equal to A over say GA XORed with B. So if I want to obtain back A, what I do is that first of all I obtain GA, and that I can easily obtain by multiplying A inverse with B XORed B, and then since GA is defined by the function inverse of A in the finite field, then I can take the finite field inverse of this. That means I can take this and so we have this function GA which is a self invertible mapping. That is, if you give it A, it will give you back A inverse, and it's a self invertible mapping, right? So therefore what I do is that I take the finite field inverse of this. If this value of A inverse B XORed B is equal to 0, then I report back 0. Otherwise I take the finite field inverse and I obtain back the output, and I call that A. Okay, so therefore we see that the AES S-Box is actually an invertible mapping. Okay. So in tabular notation, this is how the AES S-Box works. Okay, so therefore, for example, if I would like to find out or look up the value of output of 5, 3, then I take the 5th row and I take the 3rd column and I report the element ED. So therefore the output of the S-Box, if the input is 5, 3, is ED. So all these elements are denoted in the hexadecimal fashion. Shift row is a very simple operation. So what you do is that you have got 4 rows. The first row you do not shift, and in the second row you make a circular shift by 1 step. The third row you shift by 2 steps, and in the third row you shift by 3 steps. Okay, and you shift them to the left. So therefore you see that in this case the advantage of having such a shift row operation is that we shall see in our if you observe the diffusion of AES also. So the advantage, or rather the fact why the shift row is used, is that it tries to diffuse a disturbance in one of the bytes to as many columns as possible. Okay, see, for example, what you do is this, that is, you can observe this fact from this fact, that is, if you take the AES basic state matrix and if you disturbed one of the bytes and you pass it through the shift row operation, then you can see that the first byte does not get shifted, but the second byte gets shifted to this point, and this one gets shifted here, and this one gets shifted here. So now you see that you had a disturbance in one of the columns, but because of the shift row you have a disturbance in all the columns. Okay, and that is again taken up by another step which comes next. It's called the mixed column step. So in case of mixed column, what you do is this, that is you take one column and you transform this by a matrix multiplication and you obtain another column. Okay, and this is how the relation works, like how the, I mean, these are the specific thing, like if I would like to obtain the value of say S0C dash, then what I do is that I multiply with 2 the corresponding element of S0C, I multiply with 3 S1C, I take S2C and S3C and I just XOR them. Okay, and all these multiplications are in GF2 power 8. Another way of representing this mixed column operation is this, that is in case of mixed column what you do is this, that is you consider this matrix 2 3 1 1 2 3 1 1 2 3 1 1 and 2 3 1 1. So what you do is that you take this corresponding matrix and you multiply each of the column elements. Okay, so this is how your multiplication works. And why is the mixed column step placed just after the shift row? The advantage comes from the fact is that if you note this disturbance how it propagates. So now if you multiply say any one of the columns by the corresponding matrix of 2 3 1 1 2 3 1 1 2 3 1 1 and 2 3 1 1, that is the mixed column matrix, then you will see that the disturbance which was there in one column, or rather in one byte, spreads to the entire column. This particular thing spreads to the entire column, and similarly the entire state matrix gets disturbed. So therefore we say this, we refer to this combination as diffusion optimality. So in very few number of rounds actually we can see that the entire state matrix of AES gets disturbed. So the subsequent step is very simple step which is called the add round key. So you take the key and you just XOR that with the state matrix. So that concludes today's part. So you can read further things from the book of Douglas Stinson and of by Farhausen, and also I have followed certain things from the original book of Design of Rijndael written by the authors themselves, John Lehman and Vincent Ryman. So here is an example for you, that is the exercise for you, that is you can prove that x to the power of 3 plus x to the power 2 plus 1 is actually an irreducible polynomial of degree 3, and you can also work out this, that is find out the product of this multiplying this with polynomial with this polynomial in GF2 power 4, and we already discussed that in order to do a multiplication we require a modulo or rather a reduction polynomial. So you can use this polynomial as the reduction polynomial. And next day's class we shall again continue with AES and discuss about certain other things which is important for this understanding of this cipher.